Hello everyone. Today we're going to discuss about hydrogen atomic spectrum. Also, I'll talk about Balmer's formula, Rydberg's constant, and what does it really mean. Let's go ahead and get started. So, when hydrogen atoms are heated or subjected to an electrical discharge, they emit light at very specific wavelengths. Instead of producing a continuous spectrum, hydrogen produces a line spectrum, meaning only certain discrete lines appear. Each element has its own unique set of spectral lines, but hydrogen, being the simplest atom with only one electron, has the simplest and most important spectrum. Understanding this spectrum was a key step towards understanding atomic structure. The visible part of the hydrogen spectrum reveal several sharp lines at fixed wavelengths. So this was the very fascinating part. For a long time, these lines were measured experimentally, but no one could explain why they appeared where they did. The breakthrough came when it was discovered that these wavelengths follow a precise mathematical pattern. The wavelengths of the visible hydrogen spectral line are described by what we call Balmer's formula. Let's go ahead and write it down. So I'm just gonna write right here Balmer's formula. So it's 1 over lambda is equal to R times 2 to the 2 minus 1 over 2 over 2 times 2 squared minus 1 over n squared, where we say n is equal to 3, 4, 5, 6, etc. So this is what we call Balmer's formula. So here lambda is the wavelengths of the emitted light. So this lambda actually, that's what you see on the spectrum, those lines. So those are called wavelengths. R is what we call, and then later is known as Rydberg constant or Rydberg constant. Okay, so and this equation accurately reproduces every visible hydrogen line. Each value of n produces a different wavelength that's corresponding to the different spectral line. So this set, this specific set is line called Balmer series, and it lies in the visible and near ultraviolet region of the electromagnetic spectrum. So these whole lines in the visible and near UV. So one more thing is this n is very important. So as you see here, the n is integer. So this is a hint towards quantum mechanics. So because it was way before this formula was invented, way before the invention of the quantum mechanics, but this was a good step towards a quantum, because this n represents the integers 3, 4, 5, where later in the quantum mechanics they say the energy is quantized. So I'm just gonna write the n is say first quantum numbers, but they didn't know that it's a quantum number, so they just knew that this n is just the integrals. So a key feature of this Balmer's formula is that number 2, as you see, it's fixed. This particular 2 value, it's fixed. So this means that all visible hydrogen lines correspond to transitions that end at the same lower energy level. As n increases, as n goes, just say increase, and goes high, the spectral line gets closer together, and then they eventually approaching a limiting wavelength of around lambda is equal to 364.7. That's nanometers. So this is kind of a limitation, because yeah, as you increase this n value, when you do this mathematical calculation, you get this lambda as it goes. The lambda will reach the 364.7, and that's called series limit. It's called series limit. So why? Because, however, the hydrogen spectrum does not stop at visible light. And when they did this experiment, so they saw the additional collection of lines were observed in ultraviolet and infrared regions. So, to account for all of them, Balmer's formula needed to be more generalized, or it needs to be more modified. So this is done by Rydberg formula. So Rydberg formula, or Rydberg, formula, so which describes every line in hydrogen atomic spectrum. Let's write it down. So it's very, very similar to Balmer's formula, but the only thing is, now instead of 2, now we have N1. Okay, so here you see, instead of having this 2, now we have N here. So, and there is a criteria of N2 should be higher than N1. That's the criteria that needs to be followed. So in this equation now, both N1 and N2 are integers again. So the lower the number of N1 determines the spectral series, while N2 determines the specific line within that series. The constant RH is called the Rydberg constant, one of the most precisely known constant in physics. So this single equation explains the entire hydrogen spectrum. So when n is equal to 1, when n1 is equal to 1, this fall in the UV region, ultraviolet region, and the form they will call it Lyman series. Lyman series. When N1 is equal to 2, so this equation reduced exactly to Balmer's formula. So we'll call it Balmer series in a visible region. So this is visible region, and it's called Balmer series. So when N1 is 3, the lines lie in the infrared region, or IR, and form the Paschen series. It forms the Paschen series, and higher value of N1 produce additional infrared series. So the most remarkable aspect of the hydrogen spectrum is that the behavior is completely controlled by integers. Only whole number values of N1 and N2 appear, and every spectral line corresponds to the difference between two such terms. And this structure was known as, we call it, a Ritz combination principle. So I'm just going to write Ritz combination. combination principle. Reed combination principle is observed spectral lines can be written as a difference of two allowed terms. What the formula reveals is that the hydrogen atoms do not emit light arbitrarily. Instead, only specific transitions are allowed, and each produces light with a precise wavelength. These results strongly imply that the internal structure of the atom is quantized, meaning only certain energy states are permitted. And although the formulas themselves are empirical, they point directly to the quantum nature of the atom and then set the stage for later theoretical explanation using quantum mechanics. That this is a very, very good start towards the quantum mechanics. So this gave a scientist idea of that energy is not arbitrary. It's not gonna randomly emit any energy. Its energy is quantized, only emits certain wavelengths. So this was the most important aspect of this hydrogen atomic spectrum.